Okay, our next carboxylic acid derivative is acid anhydrides. So we've seen this slide before, it just lists the relative reactivities. So acid chlorides are the most reactive. Coming in second are acid anhydrides. Now, one way to make anhydrides is to excessively heat the carboxylic acid, and then it will combine to form the acid anhydride. Now, it turns out this really only works for acetic acid to make acetic anhydride, because most carboxylic acids can't withstand the high temperatures that are required. So it may seem like, if this only works for one anhydride, why do we care about it? But this will be relevant to some of our discussion later on, the fact that it's relatively easy to make acetic anhydride from acetic acid. So a more practical synthesis requires reacting an acid chloride with a carboxylate nucleophile. And this is just another example of nucleophilic acyl substitution. So in that case, my carboxylate ion is going to serve as the nucleophile. We're going to do this under basic conditions. So I don't need a proton transfer step at the beginning. I create my tetrahedral intermediate. Then, because chloride is a good leaving group, I don't need to protonate anything before I have the loss of the leaving group. And then, because my final product is neutral, I don't need any proton transfers at the end. So in this case, we just need the basic 2 core steps of the nucleophilic acyl substitution. Now, thankfully, this video is a lot shorter than the last video on acid chlorides, because both the acid chloride and the acid anhydride contain good leaving groups. Chloride is a good leaving group because it's so big, it's able to stabilize that negative charge. The carboxylate group is a good leaving group because it stabilizes the negative charge through resonance. So all the reactions that we learned for acid chlorides apply essentially the same to the acid anhydrides. We don't need to use pyridine because we're not generating a strong base. We're going to be generating a carboxylic acid, a weak acid, as the byproduct. So this is very similar to the last slide that I had on the acid chlorides video. So we can either make the acetic anhydride, or we can make the acid anhydride more generally through nucleophilic acyl substitution, using a carboxylate ion as the nucleophile in basic conditions. Or if I specifically have acetic acid, I can make acetic anhydride by heating that up. I can go back to the carboxylic acid with hydrolysis. I can do alcoholysis, aminolysis with ammonia, primary amines, secondary amines. We can reduce it. We can stop at the aldehyde by using lithium tert butoxy aluminum hydride, and we can react it with Grignard reagents and Gilman's reagents. So these reactions, with the exception of the formation reaction, are all exactly the same as the reactions that we learned from the video on acid chlorides. So one thing that's different between the acid chlorides and the acid anhydrides is, when we think about green chemistry, one thing we worry about is atom economy. So do we have a lot of byproducts that are essentially waste? And so synthetically, very often the use of acid anhydrides is not very efficient. One, we probably had to make it from the acid chloride to begin with, and since we can basically do all the same reactions, it just adds another step. But then we also have a lot of wasted material, right? The leaving group is essentially being wasted, and so we're wasting all of these atoms as byproducts, and even more if the rest of this carboxylate group is even larger, whereas there's relatively less wasted atoms in the case of using an acid chloride. The one difference is acetic acid, and we talked about the fact that it's relatively easy to make acetic anhydride by just heating it up. Well, and if our leaving group, our so-called waste material, is going to be acetic acid, it's very easy to convert it back into the anhydride. So using acetic anhydride as a reagent is actually fairly convenient in an industrial sense, because our leaving group, we can just recycle it by heating it up and converting it back into the acid anhydride. And so most of the practical reactions of acid anhydrides involves using acetic anhydride. And so because it's easy to recycle it, I can just get the anhydride back by heating up the waste product that is the acetic acid. It's often used to make esters and amides. And two specific examples of where this is used in industry is in the production of aspirin and Tylenol. So here we have the alcoholysis of our acid anhydride to form aspirin. Here we have the aminolysis of our acetic anhydride to form Tylenol.